Welcome to chapters 5.4 and 5.5, in which we'll non-dimensionalize the transient heat equation. A reminder, our physical situation is a rod of length L and coordinate in the x direction, and at time 0, the entire temperature of the rod is T0. And then at time 0, we apply heat sources on either side of the rod at temperature T1, and so any time greater than T0, we've got those constant isothermal sources on either side, and so the temperature in the center of the rod is going to begin to adjust to equilibrate to that new boundary condition. So that's our physical situation, and we need to write down mathematical expressions to describe the boundary conditions and the initial condition. So we know our governing differential equation has three derivatives, three orders. It's 2 orders of the spatial derivative and 1 order for the time derivative. So we're going to need 3 conditions, 2 boundary conditions relating to the spatial derivative and 1 initial condition relating to the temporal derivative. So our function, the solution to our equation is going to be a temperature profile in which the temperature is dependent on both x position and time. So our first boundary condition, we'll look at x equal to 0 and any time greater than time equal to 0, and the temperature is going to be T1 because we're requiring that by the problem. That's something we've defined. Likewise, on the opposite side of the rod, where the x position is L, we're also applying a heat source T1 at any time greater than 0. So our second boundary condition becomes that. Finally, our initial condition is at time equal to 0. For any position in the rod, the temperature is T0. So that's T of any position x at time 0 equals T0. So those are the 3 conditions we're going to use to specify a particular solution to our problem. Now, coming back to the governing equation that we derived, we've got 3 variables, temperature, x, and time. And we're going to need to non-dimensionalize each of these. So we'll start with the easy one. X, we already have seen this once before. We use the non-dimensional parameter xc. And there's only one characteristic length in the problem, and that is L. So we just divide x by L, and that means our x value goes from, it causes c to go from 0 to 1. And that's a good characteristic for a non-dimensional parameter. Next, we'll look at theta. There's only 2 temperatures in the problem, so we know that we're going to need to evaluate the difference between them and introduce that into our non-dimensional parameter. But the question is, should the denominator be T0 minus T1 or T1 minus T0? And those are our 2 candidate expressions for theta. They're written in such a way that both of them would go between theta equals 0 and theta equals 1. And in just a second, I'll show you how to decide between the 2 options. Finally, our time coordinate, we'll call it tau. It's going to be the time divided by some quantity that has units of time. And this is a little more challenging because there's not a characteristic time that's obviously given by the problem. So we have to find some kind of an expression that has the same units as time. And what you'll notice is that our coefficient alpha, we discussed already, it has units of meters squared per second. So that means 1 over alpha has units of time per length squared. So if you let our characteristic time be L squared over alpha, you get a quantity that has the units of time. It seems a little abstract, like, why did we make that up? Well, because it works. this is going to be our characteristic time, and we'll plug it right back into our expression for tau. And when we do that, again, we're dividing by t star, so we're multiplying by alpha over L squared. But we've created a non-dimensional parameter that relies on physical properties of the system. So this is a good start to our non-dimensionalization. Now, I said we were going to come back to theta to decide which of the two expressions to use. And what we'll do is have a look at our boundary conditions and the initial condition to decide. So again, here are our two boundary conditions and our initial condition, and here are our two candidate expressions for theta. Which to use, case 1 or case 2? Well, for case 1, if we were to non-dimensionalize using this definition, if you plug, for the first boundary condition, t1 into that expression, theta equals 0. For the second boundary condition, theta also equals 0. And for the initial condition, theta equals 1. Okay, so what happens if we do the same thing for case 2? In this case, we get kind of almost a symmetric result where theta equals 1 for both of the boundary conditions and theta equals 0 for the initial condition. So which one do we choose? Well, when theta equals 0, that's a homogeneous boundary condition. And you'll kind of remember from last week that when you have a homogeneous boundary condition, it can really simplify the problem. So case 1 has two homogeneous boundary conditions. And so we're going to choose that form of theta to use just to help simplify our maths. So going ahead with that form of theta, we rewrite our dimensional equation, and now we're going to non-dimensionalize it. And we'll start by expanding that temperature derivative with respect to the spatial coordinate. That is d dx dt dx. The time derivative is the same. It's just a first order derivative. And next, we're going to apply the chain rule to start expanding our real dimensioned coordinates into our non-dimensional coordinates. So our d dx becomes d dx dx. Our dt dx is now a dt d theta dx, dx dx. And likewise for our time derivative, we differentiate temperature with respect to theta, theta with respect to tau, and tau with respect to t. So that's the expanded form of our governing equation using our new coordinate system. And now we just have to substitute in for each of those transformational pairs what that value is. So, for example, dx dx is equal to 1 over L. So we plug that in, and we do that for the temperature pairs and for the time pairs. And our governing differential equation can be simplified now, collecting the constant terms on each side of the equation. What we see is that the constant term is the same for both sides of the equation, and so it cancels out, which is a glorious simplification. We're left with the expression d squared theta dx squared equals d theta d tau. And that is an example of a non-dimensionalization which has removed a constant, and so it's actually simplified the problem. And then coming back to our boundary conditions, we have, for the theta that we've chosen, the non-dimensional form, we have two homogeneous boundary conditions and then our initial condition, which is not homogeneous, but it's still a relatively simple form. So these are the equations. Well, this is the equation we're going to solve, and these are the conditions we're going to use to do it. So I will see you in the next session for stepping through that process. Thank you.